well-known person in air quality management area. Next, we have almost all eminent speakers. The last lecture was given by Dr. Ajay Deshpande, is again an adjunct faculty at IIT Bombay. And now this lecture is by you, and I request Lakshmi to introduce you, and then over to you for the talk. Thank you very much. Lakshmi, can you introduce the speaker?
Yes, sir. Thank you, sir. Good evening, everyone. Welcome to Air Quality Management Lecture Series for the month of January. It is my pleasure to introduce the speaker of today's lecture, Dr. Denise L. Mauzerall, Professor, Environmental Engineering and International Affairs, Princeton School of Public and International Affairs, and the Department of Civil and Environmental Engineering, Princeton University, Princeton, New Jersey, USA. Dr. Denise Mauzerall conducts scientific research that informs the development of far-sighted energy and environmental policy. Her research examines opportunities to simultaneously reduce air pollutant and greenhouse gas emissions and evaluates the resulting co-benefits for climate, air quality, public health, and food security. Dr. Mauzerall has published over 100 papers on environmental and energy topics in top research journals. She served on the U.S. Environmental Protection Agency's Chartered Science Advisory Board, was on the Executive Advisory Board for the Institute of Advanced Sustainability Studies in Germany, spoke at the World Economic Forum in Switzerland, and has been contributing author to the Intergovernmental Panel on Climate Change. Dr. Mauzerall is jointly appointed in the School of Public and International Affairs and the Department of Civil and Environmental Engineering. She is associated faculty in the Atmospheric and Oceanic Sciences Program, the Geosciences Department, the High Meadows Environmental Institute, the Princeton Institute for International and Regional Studies, and the Center on Contemporary China at Princeton. Dr. Mauzerall received her bachelor's degree in chemistry from Brown University, a MS in environmental engineering from Stafford University, and a PhD in atmospheric chemistry from the Earth and Planetary Science Department at Harvard University. Today in the lecture, Dr. Denise L. Mauzerall will be talking on the topic Air Pollution Trends in India, Disentangling the Role of Meteorology and Changing Emissions. The talk discusses how the changes in PM 2.5 is quantified, and it explores the role of meteorology in driving the observed trends. The study reveals the importance of disentangling the role of meteorology when assessing the short-term effectiveness of emission control strategies, and highlights the critical role of stringent emission control policy in driving long-term and persistent pollution reduction. The lecture will also cover some recent work focused on opportunities of co-benefits for air quality and greenhouse gas emission mitigation of various interventions in the residential, power, vehicle, and industrial sectors of China. With great pleasure, we welcome you, ma'am, and over to you.
Thank you so much. It's my honor to be able to speak with you all. It's a real pleasure to have the opportunity to share some of the work that we've been doing on India with people in India. And we welcome comments and suggestions on what we've been doing. The work that I'm presenting today is unpublished for the most part. The first part that's on India, we're preparing manuscripts right now, so your input is most welcome. Let me share my screen, and I think, okay, you can see the screen now?
Yes, we can see you.
Okay, great. So again, thank you for having me. I'm going to talk about air pollution trends in India, trying to disentangle the role of meteorology and changing emissions. I'm joined in this work by 3 postdocs. 2 are currently in my group whose work I'll focus on today, Dr. Yuan-Yu Shi and Dr. Mi Zhou, and a former postdoc, Dr. Disha Sharma, who started some of this work analyzing surface air quality measurements from the CPCB network. So for some reason, I'm not being able to advance. Let's see. There we go. Okay, so as you well know, India is facing huge challenges in improving air quality. It has 14 out of 20 of the most polluted cities in the world. 1.7 million premature mortalities are estimated to be caused by air pollution in 2019, and a total loss due to air pollution was 1.36% of Indian GDP. You can see here that relative to the World Health Organization standard for PM2.5 of 5 micrograms per cubic meter, India exceeds it by 7 to 10 times, and is really highlighting, especially in northern India, some of the worst air in the world. The National Clean Air Program was launched in 2019, and its objective is to reduce PM2.5 by 20 to 30% by 2024 compared to 2017 in over 120 non-attainment cities. And what you can see here is the data from the Indian Central Pollution Control Board Continuous Ambient Air Quality Monitoring Network from 2015 here through 2019, which is data we analyzed in a paper that came out in 2021 by Dr. Sharma and myself. And you can see a few things here. First, that the air quality in the Indo-Gangetic Plain has appeared to improve, and that the number of stations have greatly increased. And you can see now we're you're over 300 air quality monitoring stations across India. So there's been an observed decrease in wintertime PM2.5 pollution. Here you can see 2015 up through 2021 with a dramatic reduction in northern India from concentrations in winter averaging over 200 to now averaging more in the range of 100. So the 2017 is the base year for the air quality program. And you can see here a visible decrease between 2017 and 2021, decrease of it from 105 average to 72 micrograms per cubic meter average in winter. This is another way to look at the data distribution. This is a probability density function showing the frequency of a particular concentration on the y-axis and the concentration on the x-axis. And so you can see how in 2015, the tails were much heavier. 2015, 16, 17 in orange, very high concentrations were frequently measured, whereas now in 2020, 21, the concentrations at the high end have become much less frequent. There's a greater frequency of meeting the 60 micrograms per cubic meter Indian 24-hour PM2.5 standard, and still relatively infrequent occurrence of air quality that meets the World Health Organization standard. But overall, you can see a substantial decrease in severe and very poor air quality over this period from 2015 to 2021. So really, there's been success, over 30% PM2.5 reduction in 2021 compared to 2017. Very poor and severe air quality days have decreased by about half from 2019, in 2019 to 2021 compared to 2015 to 2017. And yet we have a question, why? What has driven these decreases? Is this entirely due to reductions in emissions through environmental policy, or is it also influenced by changing meteorology? And so is it emission reductions? Is it changes in meteorology? If it's changes in meteorology, we know that stagnation strongly impacts surface PM2.5 concentrations, and that meteorology and air pollution concentrations through their effect on radiation affect the frequency and intensity of stagnation events. So aerosols in the atmosphere will both reflect and absorb incoming solar radiation and hence affect inversions and hence affect stagnation. And so we'll start by trying to look at these factors to determine which ones have influence and relatively how large are those influences. So here what you're looking at are in color global emission inventories, which have now focused on the India region in these plots. And you can see agriculture, energy, industry, residential, and transportation plotted in colors, and a trend of increasing emissions from 2000 to 2020 across the board. In red, you see satellite observations of column concentrations of SO2 and NOx. And you can see from 2017 onwards, there has been an apparent decrease in column concentrations of SO2 and NOx. And a slight decrease here in PM10 emissions, and maybe perhaps a slight decrease in PM2.5 emissions as well. But these are small changes, and so perhaps only 10% or so of emission reductions have occurred since 2017. So that's not enough to explain the 30% reduction that's observed in the surface concentrations. So air stagnation leads to elevated surface PM2.5 levels. We can take as an example the United States. Here what you're looking at is the concentration of PM2.5 shown here in color, and the enhancement in PM2.5 that's observed on days that are stagnant compared to days that are not stagnant. And this is using the US metric for stagnation days, and we'll talk about later about whether that actually is applicable for India or not. But what we clearly see is enhancements in PM2.5 when the air is stagnant and the inversions are trapping pollution close to the surface. We can look at another study that focused on northern India, and here low surface wind speed episodes increase PM2.5 in northern India in winter. You are looking here at a difference between PM2.5 concentrations on low wind days versus high wind days. The circles are measurements, and the squares are model output. And generally, you can see a significant enhancement on days that are low wind compared to days that are average wind. So we'd spent a lot of time looking at the US air quality, the air stagnation index, and trying to see whether we could make it work for northern India. This is work that Dr. Meet Ju is leading at the moment. And we look at key components of stagnation events, their threshold, and whether they're applicable to India. So these are the components that were, the thresholds that were used in the US. So horizontal dispersion capability, 10-meter wind speed less than 3.2 meters per second. This seems to be applicable for India. Total precipitation less than 1 millimeter, because it's important for wet scavenging. That also seems important for India. And then vertical dispersion at 500 hectopascal wind speed of less than 13 meters per second. And that does not seem to work for India. Here you can see in this figure, in brown, PM2.5 concentrations, and in black, wind speed at 500 hectopascals. And there doesn't really seem to be a correlation or tracking of stagnation, PM2.5 and wind speed. So we went to look for other metrics to determine stagnation episodes. And what we found was for vertical dispersion capability, the current proxy in the US is used as 500 hectopascal wind speeds. What we found was that a better proxy is to use a temperature inversion in the lower boundary layer. And this temperature inversion is between 925 hectopascals and 2 meters. And so here you're seeing a comparison of the correlations between PM2.5 concentrations and 500 hectopascal wind speed. And you see there's basically no correlation. The black crosses means insignificant correlation. This is in winter across India. And here you see a correlation between daily PM2.5 concentrations and this temperature inversion in the lower boundary layer. And we're getting excellent correlation at many sites, with correlations typically over 0.6 in northern India. And so we then substitute this temperature inversion as a proxy for determining stagnation events. Okay, so then we want to try and understand how much does meteorology contribute to the PM 2.5 decrease in 2021 compared to in 2017. What you see here on the left is a time series for December to February. First in brown is 2017, and then in blue is 2021. And you can see systematically through the winter, 2021 was cleaner than 2017. We then look at the inversion, and we find that PM 2.5 is strongly modulated by inversions. You can generally see that 2017 had more inversion episodes, and 2021 had less. You can see that when there was better ventilation in the lower boundary layer, the concentrations in 2021 were lower. Here again, you see the same effect. There's also more frequent and intense precipitation in 2021. And here you can see this precipitation also correlating well with the lower PM 2.5 in 2021. And so precipitation and ventilation contribute to the lower PM 2.5 in 2021 than in 2017. And you can see here these marks really allowing you to visualize the correspondence between inversion, precipitation, and concentrations. And then finally, when we look at wind speed, we really don't see a significant difference in average wind speeds across the years. And so again, that supports the idea that this inversion is a much better metric to use in India to evaluate stagnation events than wind speed. Okay, so changes in stagnation explain about half of the observed PM 2.5 increase from 2017 to 2021. Here you can see that stagnation is averaged over all the monitoring sites in this box here. And in dots here, you can see PM 2.5 concentrations. In green, you see stagnation-derived PM 2.5 and the trend that results from that. And that trend is about 4.3 micrograms per cubic meter per year, whereas what we see for PM 2.5 concentrations alone is a trend of about 7.2 micrograms per cubic meter. And so that is less than twice as large as what we get from just the stagnation-derived change in PM 2.5. Circles here are showing measurement stations that were operational from 2015 to 2017, which are not plotted here, but which actually appear to have higher concentrations and don't correlate as well with stagnation. And this is something we have not yet been able to really figure out what's driving that, whether that's because there's some issues with early measurements, whether stations have moved locations, whether stagnation doesn't explain things this early. And so thoughts on what might cause this would be most appreciated. Okay, so we then go on to construct a more sophisticated method to identify stagnation over northern India for each season. So we're using two primary criteria. The first criteria is that the weather is dry, that daily precipitation is less than 1 millimeter. And the second criteria is basically plotted here on these figures, is that there's a strong inversion in the lower boundary layer, as we've discussed, and that there's weak surface winds at 10-meter height. And if both of these criteria are met, you fall above this line. This is showing each of the seasons: pre-monsoon, monsoon, post-monsoon, and the winter season. So above the curve are stagnation days, below the curve are non-stagnation days. And we can look at winter when the air pollution is worst. And in each of these cases, we're plotting an anomaly. It's the normalized It's the change in concentration for daily PM10 for each station, normalized by the seasonal mean over this period on dry days. And when you do that, you can see that during stagnation days, there's an enhancement relative to the seasonal mean in PM2.5 of 10 to 20%. And on days that are not stagnant, there's a decrease in PM2.5 concentrations of 10 to 20%. So this seems to really indicate how important stagnation events are in determining relative changes in PM2.5. We can see here how monthly variations of stagnation frequency are well correlated with observed PM2.5 concentrations across seasons. What you're seeing here is first for Delhi and then for the Indo-Gangetic Plain. Plotted in red are observed PM2.5 concentrations. And so that's here. You see this line in red. The stagnation frequency identified in this study, the improved metrics that we're using are plotted in black. And you can see very good correlations both in Delhi and for the Indo-Gangetic Plain. But the stagnation frequency that's used in the United States that works well for us does not correlate well at all with the observed PM2.5 concentrations. Okay, so that is the analysis so far of current situation and how PM2.5 has responded to changing emissions in meteorology from 2017 through 2021. But a question then is, how will future changes in climate and in air pollutant concentrations affect stagnation and surface PM2.5 concentrations? And to examine this, we turn to climate model simulations to try and examine future climate impacts on stagnation episodes. The climate models that we use are part of the Coupled Model Intercomparison Project Phase 6. And this model intercomparison project is intended to allow various climate models from around the world to compare against each other using exactly the same inputs. And the goal is to better understand past, present, and future climate change arising from both natural and anthropogenic forcing of the climate system. We've utilized specific simulations that were part of CMIP6, and the ones that we examine look at the theoretical increases in carbon dioxide and what that does to concentrations of air pollutants and meteorology, historical changes in greenhouse gases and air pollutant emissions, starting from the past and going to the present, and then future emission scenarios starting in the present and going to the future to try and examine what will happen going forward. So to do this, we wanted to first understand the impact of carbon dioxide on stagnation. And to do that, we used two simulations, a control simulation, which maintains carbon dioxide at pre-industrial concentrations and aerosols at pre-industrial concentrations. And then a 1% CO2 simulation, which increases carbon dioxide concentrations by 1% a year from pre-industrial to 150 years forward, which leads to a 4 times pre-industrial concentration, which is not a realistic scenario for the real world, but does allow a careful analysis of what impact increasing CO2 would have on forcings. And then a historical simulation starting in 1850 through 2019, driven by the historical changes in aerosol emissions, with everything else kept at pre-industrial levels. So for the theoretical analysis, we look at the impact of this 1% increase each year in CO2, which leads to 4 times pre-industrial CO2 levels, we look at the effect it has on meteorology. So this is the effect it has on inversions, on 10-meter wind speeds, on precipitation, and on stagnation. And you can see that there's increasing CO2 dramatically like this has a modest decrease in inversion, a larger decrease in surface winds, a slight decrease in precipitation, and as a result of these factors, a slight increase of about 20% in stagnation occurrence over this very dramatic rise in CO2 over 150 years. And this is a rise we hope the world never sees. Like I said, it's simply to try and zoom in and better understand the effect on meteorology. We then use the simulation where we start at pre-industrial and then allow the aerosol concentrations to increase according to what has been observed historically. And here you can see this, the aerosols, the black line is PM 2.5 and the dashed line is black carbon multiplied by a factor of 10 just to make it more visible. And what you can see is that increasing these aerosols made inversions much more intense, particularly recently when the air pollution levels started to increase rapidly. The wind speed didn't change much. Precipitation may have decreased a little bit, and the stagnation occurrence then increased by about 10%. And so the presence of air pollution does affect the inversions in the lower atmosphere and then does increase the stagnation occurrence. And you can see that increase occurring most notably in about the last 25 years or so. Okay, so then we go on to look at the future scenarios and try and understand the relative importance of warming and pollution in driving the changing surface concentrations of air pollutants. Here we're looking at two different scenarios. This is SSP3 7.0, which is a high warming scenario, 7 watts per square meter, about a 3.5 degrees Celsius increase over the century, and high pollution, meaning high SO2, high black carbon concentrations. And SSP1 2.6, which is low warming, here you can see high CO2 emissions in red, low CO2 emissions in blue. SSP 2.6 is low warming and low pollution. This is a very optimistic scenario. This is stopping at about 1.5 degrees Celsius increase in global average temperature. And sadly, we're approaching about 1.2 degrees already. So this is a very optimistic scenario. If we look at the differences between these two scenarios, we find our stagnation days are much higher when you have high warming and high pollution than when you have low warming and low pollution. And then we can look here at what happens to the concentrations as a result. And you can see that relative to the change in emissions, the concentration is much higher when you have these high stagnation days. And the enhancement in concentrations is much smaller when you have lower stagnation. And so you can see that both warming and high pollution lead to an enhancement in concentrations, and less warming and lower pollution lead to a lower enhancement. Again, we still have the question, which is more important, the change in meteorology or the change in emissions? So we then go and look at two high warming scenarios. And so here, this is what we looked at before. And here we've now gone to SSP 8.5, which is about 4.5 degrees Celsius increase in global average temperature. Again, something we hope does not come to pass. Here you can see that this is high pollution in SSP 7, And low pollution, particularly after mid-century, the pollution drops dramatically in these scenarios. And so we see changes here in stagnation days as well. This is stagnation increases relative to 2015, and in SSP 5, 8.5, it first increases and then decreases. And so what we see here is that the enhancement in concentrations are largest with high pollution and high warming, and the enhancements in concentration relative to the emissions is much lower when you have the low pollution, even when it's coupled with high warming. And so what we find from this is that in the future, reducing air pollution will enhance the reductions that you would get through just reducing emissions. It'll provide a win-win opportunity to reduce stagnation and hence enhance reductions in surface air pollution levels. So this is good news. But what we've seen is that there's also an effect of climate. So let's look at some takeaways from this larger study before we move on. So you saw, and I'm sure you're well aware, that PM2.5 air quality improved from 2015 to 2021, with frequency of very high concentrations dropping and frequency of concentrations which meet the 24-hour air quality standard of 60 micrograms per cubic meter in India increasing. You saw how we established an improved method to identify stagnation over northern India using temperature inversion, surface wind speed, and precipitation. And that provides a clear delineation between daily enhancements relative to the mean concentration for PM2.5. Our stagnation index better correlates with monthly PM2.5 levels in India than the US metric does. And you can see here the red and the black lines are monthly PM2.5 concentrations and the stagnation frequency using our new metric for stagnation in India. We find a decrease in stagnation days contributed to over half of the PM2.5 decrease observed from 2017 to 2021 in northern India. And so emission decreases are important, but there was a beneficial increase in ventilation over this period, which helped meet the new air quality targets. A takeaway for the future is that there's a win-win opportunity here. Theoretically, increases in global CO2 levels and regional aerosol emissions both lead to more stagnation events in winter over northern India. And that what we found is that in the future, reducing air pollution and CO2 will provide a win-win opportunity to reduce stagnation and enhance surface pollution reduction simultaneously. So this brings me to the end of the first part of my talk. The second is much shorter and will really be a schematic overview of some of the other work my group has done, which has largely focused on China and on evaluating opportunities to simultaneously address air pollution and greenhouse gas mitigation. As you saw, one of the key conclusions from the first part was that reducing air pollution has the ability to further enhance future reductions in surface concentrations, and then also reducing climate change will have benefits as well. So the question becomes, how do you best do both together? There's ways in which air pollution can be reduced that actually cost energy and increase carbon dioxide and other greenhouse gas emissions. And there's ways in which it can be done that reduce both greenhouse gas emissions and air pollution. And let me just quickly walk you through some of these ideas. So our objectives have been to evaluate opportunities in the power and the transport and the industry and residential sectors to reduce air pollutant emissions and resulting concentrations. By doing that, to reduce premature mortalities due to air pollution, and we try and quantify those lives saved, and to reduce also associated greenhouse gas emissions. And we look not only at CO2, but at methane and nitrous oxide. And so we report this typically in terms of CO2 equivalents. And some mitigation strategies have co-benefits. So briefly, for the power sector, an example of co-benefits would be to replace a coal-fired power plant with solar panels. That would eliminate the emissions from the coal-fired power plant of air pollutant emissions and of carbon dioxide. And solar panels or windmills don't emit, don't directly emit either. For the transport sector, it would include electrification of vehicles using electricity that is generated from non-fossil sources. From industry, it could include improving efficiency or building synergies between different industries. For the residential sector, in China, we've looked a lot at the role that small stoves like these here contribute to fine particles, and then at how various substitutes can reduce air quality, can reduce air pollution, and that would include using natural gas, using electric heaters, and those electric heaters could be resistance heaters or air source heat pumps. And what we find is that all of those options improve air quality, but using resistance heaters actually increases your CO2 emissions if you're using a coal-intensive grid, and using air source heat pumps, which are extremely efficient, 3 times more efficient than electric resistance heaters, dramatically reduces both air pollution emissions and CO2 emissions, particularly as the grid decarbonizes from one that's coal intensive to one that's dominated by renewable energy. So just a quick schematic of our approach here. We look at current emissions from various sources, and then we look at emission reductions that occur through various interventions. Here I'm using an example of windmills substituting for coal power plants. Then we look at the reduced air pollution that occurs as a result of that substitution, and then we quantify the reduction in CO2 emissions and the health improvements that result from the interventions. So this is again just a schematic, but if we look at the increased efficiency and end of pipe controls, increasing efficiency would decrease emissions of air pollutants and greenhouse gases. End of pipe controls would decrease emissions of pollution, but potentially increase emissions of carbon dioxide. So you in total get a reduction, a small reduction in deaths and a small reduction in CO2 emissions. If you electrify with coal, you get a larger reduction in air pollutant emissions and associated deaths because it's easier typically to control emissions from a central power plant than lots of small sources across the country, like, for example, the use of solid fuel in the residential sector. And you get a small decrease in CO2 emissions because often electric motors are more efficient than direct combustion. And then finally, electrification with coal plus renewables would be much better. You would eliminate your emissions from the portion of electricity you're generating with renewables. So you reduce your air pollution concentrations and premature deaths more. And the use of renewables would dramatically reduce your emissions of carbon dioxide. And so this would be a particularly attractive option as a transition away from fossil fuels. So in this work, we try and put these various interventions on a graph like this, where we look at synergies and trade-offs between reductions in air pollution, in interventions where reductions in air pollution concentrations and resulting premature mortalities decrease, with reductions in CO2 emissions, or potentially a penalty, a trade-off, increases in CO2 emissions. So trade-offs or synergies. And so, as I mentioned, trade-offs might be using electric resistance heaters instead of small coal stoves, which would increase your CO2, even though it cleans up your air a lot. Synergies would be powering your vehicle sector with renewably generated electricity. Okay, so this is sort of the framework that we try and think about things, because it's so important in today's world to really try and figure out how we can leverage co-benefits between air quality improvements and greenhouse gas mitigation, and not think of these things any longer as one or the other, but bring them together and look for co-benefits between the two. The last thing I'd like to talk about is actually a specific project that we did looking at co-benefits for solar photovoltaic electricity generation of improving air quality. So electricity generation by solar panels is reduced by fine particles in the air and by fine particles in dust that deposit on the solar panels, because both of these reduce the amount of solar energy that can penetrate into the solar panel and be converted into electricity. So global reduction of solar power generation efficiency due to atmospheric aerosols and panel soiling occurs. And you can see here a figure looking just at the solar irradiance of fixed angle panels around the world due to atmospheric aerosols and clouds. And you can see that India has a fairly robust solar irradiance reaching the surface, about, say, on average, 5 kilowatt hours per square meter per day, with northwestern India, particularly Rajasthan, having some of the highest levels of radiation. We then look at, well, what about deposition onto the panels? And we look at how capacity factors, which is the actual annual electricity generated divided by the maximum possible annual generation, how that might be reduced by dirt on the panels. And you can see here that in some parts of the world, the capacity factor is reduced dramatically. If you look, for example, at North Africa, this is the capacity factor if the panels are perfectly clean. The capacity factor is about 0.25. That's because obviously the sun doesn't shine at night, and outside of noon, it's not you're not capturing as much energy. So in North Africa with clean panels, you have a 0.25 capacity factor. But if those are uncleaned, a lot of dust is allowed to settle on those panels, the capacity drops dramatically. For India, you can see a decrease of about 50%. But this reduction varies greatly around the world. So here we look at the reduction in capacity factors due to both atmospheric aerosols and panel soiling. This is atmospheric aerosol reduction caused reduction in capacity factor, and this is due to panel soiling. And this is the total of those two together. So substantial reduction. If we look at this figure, this is showing the percent increase in capacity factor if atmospheric aerosols are removed. So suddenly, magically, there was no more air pollution. And on the y-axis, it's the percent increase in capacity factors if the panels are kept clean. And this isn't magic. This can be either cleaning by people or cleaning by robots, which is something which is done in the Middle East now when they're building these large utility scale PV fields. They have automatic brushes, which once a day will brush off the dust that's landed on the panels. And you can see here for India, India would experience about a 25% increase in solar power generation if magically there was no more air pollution, but about a 50% increase if solar panels were kept clean all the time. Okay, so here's another way to look at this. Here you're seeing the benefit that India could have for increases in capacity factors if it kept solar panels clean in different parts of India. And you can see, so if the panels were kept clean all the time, the capacity factor could be increased by over 50% in northern India and western India, and by almost 50% in eastern India. This is showing here quarterly cleaning, monthly cleaning, and the top bar is always clean. So again, here's another win-win opportunity. You have, if you increase electrification and use of renewable energy, you'll get a decrease of air pollution and greenhouse gas emissions, leading to improvements in public health and also in climate. The air quality improvements lead to better public health, but also to increased solar electricity generation efficiency because more solar energy reaches the panels. In resource-abundant regions with substantial pollution, cleaning PV panels can increase electricity generation by more than 50%. So a virtuous cycle exists. Air quality improvements increase efficiency of solar PV generation. More PV generation and electrification will reduce emissions of air pollutants and carbon dioxide, improving surface air quality and also improving public health. So with that, I'd like to end and thank my two postdocs. This is Dr. Mi Zhu and Dr. Yuanyu Shi, who contributed the majority of the work that I presented today. This is the rest of my group, currently working on a whole spectrum of different things, but I'd like to just highlight two PhD students who are focused now on Indian power sector and ways to help decarbonize the power sector. With that, thank you so much for your attention. It's been my pleasure to have the opportunity to tell you a little bit about what we do. Thank you.
Yeah, thank you, Professor Denise. It's an excellent talk. Before we take up some questions, maybe I request all of you, all of the participants to start their camera. We will have one photo and then we will start discussing about the questions so that you will also get some time for to have some break before answering the questions. Okay, well, okay, Swaroop, you can take the picture.
Yes, sir, I can. Shall I wait for some time or?
Yeah, just we'll wait for some time. Yes, others just a few more.
Yeah, I guess people are just putting their cameras on now. It's nice to see your faces.
Okay. I request all to start the camera so that we can just take one picture with Professor Denise.
Everybody smile, please. Taken, sir.
Okay, 1 minute.
Thank you.
Okay, great. So I'm
Yeah,
happy
thank
to
you.
take questions.
Yeah, Professor Denise, there some questions are there in the chat box. Will you able to read that? Or,
Oh, okay.
Yeah.
Let me take a look. So maybe someone can ask the questions. There's an
Okay, I'll just put the one first. The question is from Sanjay. The question is about how you have studied the air quality data from CPCB monitors for accuracy because our change in number of monitoring stations over the study period because this could be some change in number of stations or maybe the locations might be changed. Would more or better measurement of PM 2.5 have also contributed to decrease along with stagnation and rain events? So it's basically
so that's a super important question, and we paid very close attention to it and went through a really stringent air quality control analysis of the hourly data from CPCB. Some of that process is described in the paper by Sharma and Mauzerall I mentioned at the very beginning. And if people go to my website, you'll be able to find that paper there. But there was a lot of challenges in using the data. There's definitely cases where there were spikes in time series, there were spatial anomalies within cities, particularly for compounds like ozone, which we were unable to really figure out why some stations that were next to each other had concentrations that were differing by a factor of 2. We thought maybe it was a unit issue, and we couldn't get to the bottom of it. So we've set aside the ozone analysis. If people have information on that, we would love to know. We did careful analyses so that if you see, we always take the same stations across the time period. So if we're analyzing data that starts in 2017, we'll only use stations that existed from 2017 to 21 for the analysis. We won't add them all. We won't average them all together. Actually, I see Dr. Miju added some comments here to answer that question. So actually, if you guys, Dr. Miju or Yuan Yu, she, who is the other postdoc who was important in this work, want to speak now, that'd be fine, and discuss a bit more about that question.
Okay,
I think he's put a fair bit of information here also beyond what I said.
Okay, yes, Mizu has already given a lot more information.
Yeah, that's great. I just noticed I scrolled down.
So quite look at it. I think Sudhir's question, I just thought maybe I'll try to look at it, because this, the pandemic also helped to understand how the reduction in anthropogenic emissions, particularly if you try to look at it, transport emissions have been significantly reduced. Some of the industrial emissions have been significantly reduced. Of course, the power plants has no change because the energy generation was more important. So what is your comment on looking at this anthropogenic emissions? Will some aspect have been reduced, and how do we look at it in terms of improving the air quality? Because the emission rate has been increased, and the stagnation and aspect which you rightly mentioned. How do we look at it? This anthropogenic emissions happened because of this pandemic activities. Means what percentage?
Yes, so that's an excellent point. The pandemic probably reduced the emissions during that 2020-21 period, and that probably was a contributing factor. We haven't looked at that explicitly. We looked only a little bit at some of that data in a separate effort, which we have not incorporated here. So that's actually a really excellent point for us to think about the pandemic reductions. I guess the pandemic periods were, the shutdowns in India were fairly brief, but I'm familiar with the NO2 satellite data, which showed dramatic reductions in NO2 concentrations, column concentrations during the shutdowns. How that actually affected other primary sources of PM 2.5 is less clear, because probably residential sector emissions continued, agricultural sector emissions continued, but some power sector emissions continued, but certainly some of the vehicle emissions decreased. And so that's a good point to think about the role that the COVID shutdowns played on the decreasing PM 2.5.
Yeah. So I have another question. So, in India, we started looking into the carrying capacity and basically try to understand how much, meteorology helpful in addressing the emissions contributed by various sources. So now we're considering the context. There is an equations to look at it: recirculation, stagnation, and ventilation. And important parameters is the temperature, and also the mixing height, and also the wind speed. And you rightly mentioned about the wind speed and the temperature, which we have taken care. How do we correlate with the mixing height component or boundary layer? Because that is another aspect which also influences significantly in terms of air quality in an urban area.
So the mixing height, you mean the boundary layer height?
Yes.
So actually, I'll turn that question over to Meet Ju, because he's the one who's looked most carefully at the
Okay.
inversion metrics. I mean, I think he found that inversion between 925 hectopascals and 2 meters was the best indication. But Mickey, do you want to go ahead and say something on this?
Okay, 1 minute. Swaroop, can you just make Mizu also a co-host so that he can answer some of the questions, and Professor Mukesh Sharma is here, and I'm very glad to see him. Can you also make him co-host so that he can also participate in the discussion?
Yes, all can unmute themselves. I have put it the
Yeah.
option.
Yeah, Mizu, can you just go ahead answering the question?
Yeah, thank you. Yeah, I'm unmuted. Yeah, as for the boundary layer, like we find that the boundary layer height is a good predictor for PM 2.5 over winter and autumn in northern India, but boundary layer is not that good to predict PM 2.5 over summer and springtime. So that's why we choose another metric, the temperature inversion, because temperature inversion we find has a consistent relationship with surface PM 2.5 and boundary layer, but the relationship between boundary layer and PM 2.5 will switch across different seasons. So that's one of the reasons we choose the temperature inversion, because it's more robust and consistent.
Okay, thank you, Mizu. Dancy, I have another question. I thought I'll take some, your views. In terms of measurements, basically, if we try to look at it, the easy to measure is the pressure and surface temperature, and of course, wind speed to some extent. So can't we not relate, the air quality with respect to the pressure, because that will also influence the air circulations in the local as well as regional aspects. So do you have some advice or comments, because there are many young researchers attending this talk? So what is your view? Because pressure is easy to measure. I look at it that way, because of course it is also not very drastically. Do you have some comments on that?
Sure, thanks for your great question. Yes, we take a look at the ordinary meteorology variables, including pressure, wind, temperature, humidity, so all of them. But the reason we just choose the wind speed, precipitation, and temperature inversion is we want to understand the air quality meteorology interaction from the perspective of atmospheric dispersion. So as we included in our slides, we have 3 processes for the atmospheric dispersion. The first process is precipitation, the wet scavenging. So that's why we use precipitation as a proxy. The second one is vertical dispersion. So that's why we use surface wind as the proxy. And the third one is the second one should be the horizontal dispersion. So that's why we use the surface wind speed. And the third one is a vertical distribution. So that's why we are trying to use either boundary layer height or the temperature inversion. And we believe that the pressure is easy to measure, but the changes in pressure is associated with other factors like the wind or the temperature inversion. And the pressure itself cannot be easily identified as a measurement to atmospheric dispersion. So that's why we do not use pressure in our study. But I believe that I have seen many studies that has tried to understand the relationship between PM 2.5 and the surface pressure. And in some places, they do have good relationship. But when we want to look at the stagnation events, we just want to select variables that based on the 3 criteria as I mentioned. I hope this it's an answer to you.
Yes, I think you answered the you put right perspectives of why the pressure, temperature, and humidity role of there in the particulates dispersion. No, I mean, that leads to another question. I mean, the particulates number concentration, I'm just trying to look at it these days. They are also looking at the gaseous phase particulates to the larger size particulates. And when you try to look at it, you know, the deposition aspect also looking at in terms of the size fraction. Now, this when you try to look at it from the you know, the rainy events or maybe the stagnation events, whether any particle formation aspect also have you looked into that, and it make any influence in terms of removing the particulates from the environment?
Yeah, thanks for your question. Like, this is more about the atmospheric chemistry and the new particle formation. And unfortunately, our study do not focus on this part. Like, we just want to understand the changes in meteorology on regulating the dispersion of air quality. So I think our study is focused on atmospheric physical process. So it might lack some details in the atmospheric chemistry and also the new particle formation. But and actually we only have the data from the CPCB, like it's hourly observation for PM 2.5 or other gas species, and we do not have more detailed data to help us to understand the atmospheric chemistry or the new particle formation. If we want to do that, we might need additional data input from India, and that will be valuable. Yeah.
Yeah. Thank you, Mezo. I think let me ask Professor Mukesh Sharma, like.
I actually think your earlier question about whether you could use the pressure was really important in the sense that if it were possible, it would be a metric that, as you point out, is extremely easy to measure and might be more widely used as a tool for informing the population of upcoming air pollution episodes. And so thinking about that more in the future about what kind of proxies might allow us to use something that's easily measured to make forecasts is a valuable thing to pursue.
Okay. Yep. Thank you. And we will look forward because pressure is much easier to measure, and particularly in country like us, a tropical environment, temperature variation is so quite different in different areas, and it is much easier to look at it how the stagnation can be quantified. Okay.
Right. Yeah. So moving from a theoretical study to something that's practically implementable is an important next step.
Yeah. Okay. I think I'm not able to reach out to the Professor Mukesh Sharma. He raised some. I think he's back. Yes. Go ahead, sir.
Well, thank you, Shiva. Thank you so much. Thank you, Professor Denise. Wonderful talk. Indeed, new ideas, a new way to look at the things, and getting some very interesting sort of results. But obviously, there are a few questions, obviously, as we analyze the data here. So if you kindly allow me to ask as to it's a bit intriguing that something worked in US in terms of the stagnation determination vis-a-vis India. Why you think that something worked there and it didn't work? Was the surface inversion was too intense here, and why do you think that the intensity of the inversion changed from 2015 to 2000 or 2017 to 2021? What are the reasons, or is just a natural phenomena?
So to answer the first question, why does it work in the US and not work in India? We haven't analyzed specifically what the reasons are, but to speculate, northern India is bordered by the Himalayas. And so that probably has an influence on 500 hectopascal wind speeds and directions. And in the US, most of our polluted regions are in the east, which are relatively free of large mountains. And so, or in the west, but prior to where the mountains occur. So it's I don't have a real answer for it. Why the inversion and stagnation seems to have changed over that time period. Dr. Yuan Yuxi did a fair bit of work trying to look at the Western disturbance to figure out what may have caused that. We didn't have a clear conclusion on it. Yuan Yu, I don't know if you want to try and say something in response to that question.
Hi, can you
You're
hear me
typing
well?
away. Oh, good. Yeah, we can hear you. I don't see your name, so I didn't know if you were still here.
Yeah, thank you for bringing up that question. So in this current study, we are focusing on understanding what is causing this observed PM 2.5 decrease during the past 5 years in the context of the National Clean Air Program. And we are eager to understand what is driving the changes in stagnation, which has been identified in this study to be part of the reason of the observed PM 2.5 decrease. And we hope to investigate on that question in another study, which is ongoing, and I hope to share more results with you later.
Thank you, Zay. So you have.
Thank you. Well, I mean, very quickly, just a comment actually. We have, we have the Air Pollution Control Agencies working very hard to reduce the emissions, and they have been successful to some extent. But they would be worried that all credit goes to the meteorology and not to their efforts. So I'm sure this is a combination of two things: their efforts as well as efforts for emission reduction and also the meteorology part. I think I just thought I'll make it a point actually.
Yeah. So I think that's a super important point. I mean, we absolutely agree that reducing emissions is absolutely crucial. There's no question that that's critically necessary. Looking at the future, our conclusion was that the meteorology is not going to save India from terrible air quality problems, that you must reduce, and that if you do reduce, you're going to get an enhanced reduction in concentrations relative to the emission reductions which occur because of the effects of the stagnation resulting from the emissions and of the particles, the concentrations of the particles in the atmosphere. And that there's a hugely long way to go before you get air quality that's healthy, right? I mean, even meeting the 60 microgram per cubic meter air quality standard for India is nowhere close. It's 4 times higher than the World Health Organization standard. So emission reductions must be reduced. And if I can ask you guys a question, I'm really interested in what does India see as the best way to improve air quality? What are the mitigation strategies that the government is emphasizing? And is that mitigation, are those mitigation efforts primarily driven by the science of what will improve air quality the most, or the cost effectiveness of different mitigation strategies, or the political ease with which the mitigation can take place? So is it science, politics, or economics that's driving the air quality efforts?
Very quickly, I think the big thing that has happened during last 4 years is that the cooking at the rural level, which was completely biomass based and wood or dung for that matter, so that has changed dramatically, and the government has tried to sort of make sure that the entire population is able to have the LPG supply, that's a gas supply. Of course, affordability is still a question to the economically weaker section. But what has happened, at least the 50% of, that's what is the survey say, that 50% of even the rural population has now started using the gas instead of the biomass, dung, wood, whatever they could get. So that to our understanding, see this huge population, and the population density in IGP is very high. You won't find it even in a place like China for that matter. So that particular thing has helped. Our earlier estimate showed that almost PM 2.5 in terms of the emission could be 40 to 35 to 40% could just come from the domestic sources, because 1.4 billion people cooking 3 meals, that was enough to cause a big problem. So in our judgment, this emission reduction has been significant. I mean, not to the level we would like it. So that's one part that has happened. The second thing is the brick kilns. Brick kilns are massive emissions in the country. So that part is still we are lacking, but we are trying that they go to a better technology. They cannot be supplied with gas and all. So second big effort in pollution control is to go for something what we call a zigzag technology for the brick kilns, because that is the second largest emission and very sort of unorganized sector actually. And the third thing is, of course, we are going for the secondary control that is more strategic and more scientific based. Especially all power plants have been, mandated now to have the SO2 control to a large extent. It's very expensive, undoubtedly. There's a lot of opposition, but I think that's the way to go forward in terms of the SO2 control. So these are the three large things happening in addition to many local actions being taken. Actually, I thought that I'll just clarify these points.
Yeah, that's fascinating. Thank you so much for sharing that. And the residential sector has been enormously important in China also. We had a paper a few years ago in PNAS showing that 40% of the fine particles in the Beijing, Tianjin, Hebei region in winter were coming from coal heaters. So it's not,
Correct.
It's the residential sector entirety, but in winter, the dominant emissions are coming from heating, not from cooking there. And it's enormously important. The Chinese were very aggressive about removing those stoves and replacing them with other heating options. And they've seen a dramatic improvement in air quality, driven to a substantial amount, also, like you're saying, for India, from improvements in the residential sector. But China is also focused across the board, on the vehicle sector and the power sector, and now beginning to also look at the industrial sector. It's interesting about the brick kilns. I've certainly heard that they're a huge source, and that's certainly also an area to think about in the future.
Yeah. Thank you, Denise. I think it was a wonderful talk. And one question I thought I should ask you too about the policy aspect. The monitoring stations set up in some of the US, cities. Are there permanent stations? Because I just look at it. In Indian context, sometime when we set up the monitoring station for a particular purpose, for example, we set up a monitoring stations to monitor the residential area air quality, but over a period of time, it was become commercialized and it became kind of a traffic, zone, and the emission characteristics completely changed. So do you have some strategies or some planning? Because I'm just trying to look at it in terms of monitoring station should not be permanent, and it meets to certain purpose for a time bound. And how do you look at it, the monitoring stations in each city, and is there any policy with the government in US? How did they look at it?
So that's a super important question, and that's actually something we've thought and worried a lot about with the Indian stations, that maybe they don't move, but the pollution comes to them, and suddenly there's a bus station next door instead of a grocery store, and the local emissions affect them. In the US, this is not my specific area, but generally in the US, we've often put our air quality monitoring stations at airports that are outside of the city. There's a lot of thought and effort that goes into making sure that their fetch is relatively homogeneous. So our stations are often not in urban centers. The ones that we use to analyze, for example, evaluate air quality models are often outside. And so we're able to assume that there's no local sources nearby. If they're in areas that are more built up, they'll put them on rooftops instead of at surface level. There's a lot of thought, I think, that goes into trying to put them in areas that will not be affected by local contamination.
Yeah, excellent. Thank you very much. Sorry, you want to answer something?
Yeah, Professor Nagendra, if you allow me to speak, I'm Rao Chitikela. I'm an independent consultant joining from Dublin, Ohio. I was a past.
Great.
Good morning, Denise. Great presentation. I was a past air regulator, worked with state of Delaware. I quickly looked up the air monitoring criteria. If you can look up under 40 CFR, 40 is the title environmental pollution
Federal Register.
Number 40. CFR is the Code of Federal Regulations. And if you see 40 CFR Part 58, it has the ambient air monitoring. And anywhere from parts 50 to 58, you will find how the monitoring stations are sited and how they have to be. And then, yes, they are, I think most of them or all of them, they have to go through the EPA evaluation analysis before selecting the station and the specs to establish a station, and the continuous monitoring stations and continuous monitoring of the data, all the NACs, all the 6 NACs are measuring the ozone, 8-hour ozone, and PM 2.5. So that's a lot of work, continuous basis. Yes, there is a certain criteria and that is available under 40 CFR. It may be Part 58, but you can your folks can look into it.
Yeah,
Thank you.
Thank you,
Yeah.
Thank you, Professor Rao. Professor Denise, I was just looking at something just to continue with what Professor Mukesh Sharma. So we have, most of the policies are, as you rightly look at it in any countries, it is all science driven. Like basically, they many studies indicates what is the characteristics of the air quality, what is the toxicity, all these aspects influencing, in particularly this biomass emissions in a rural area, also influenced with several studies over a year, over a decades. And then based on that, the government initiated Pradhan Mantri Ujjwal Ayojana. So basically that brings every woman should use cooking gas for the for the domestic purpose. So as a result, it comes down significantly. I just wanted to put you another information so that may also help you, because India is growing very fast, and many construction activities also happens, and most of our monitoring stations are just about 3 meters to 10 meters height. And what you see, the pollution aspect is only the resuspension that contributes, and particularly if you try to look at in terms of mass concentration, about 60% of the pollution is only from the resuspension. So, and if you try to look at it, the control aspect is we are trying to take several measures just because of our tropical nature. All this dust will get resuspended very fast. And probably I'm just thinking whether the standards, what you try to look at it from the, the Western countries where they have a cold climate, and maybe in the country like us, which is in a tropical environment. Do you think that, for example, WHO has given some guidelines? Should we use the uniform guidelines across, the geographical area for addressing the health risk? Or do you think that based on your experience, we should have, some different policies?
So that's a complicated question. Going back to your earlier question about should monitoring stations stay in the same locations or not. There's, I think, a strong argument for continuity in location, but that would only be useful if the location was carefully chosen initially to be able to avoid contamination from local sources in the future. And so your point that there's increasing construction happening everywhere, and that may lead to local contamination, more dust, resuspension is a challenge. But overall, I think some continuity of measurements is important where possible. Regarding whether there should be different standards in different locations, the standards should be based on human health impacts, right? What the sources of the pollution are, whether it's resuspension or initial emissions, really is secondary to what the concentrations are in the atmosphere and what was going to affect people's health. And so that's where I would leave it, I guess. I think that then, therefore, based on human health, the standards in different locations, and maybe it's just more difficult to achieve the standards in some locations than others. And one can recognize that these areas are more polluted, but I don't think the standards probably should be different.
Yeah. Thank you, Denise. I think we were also, debating on that because the air quality, we should look at it how, health impact can be associated with particularly some kind of a marker pollutant which are present in the particulates may be responsible for causing some of the health risks. Probably we should try to look at it in a different source contributing different marker, toxic elements that are responsible for causing, health risk instead of looking into the general particulates. I mean, that's what some debate is going on. Thank you very much.
That's a valuable point, because if you could identify where those toxic components are coming from, you could target mitigation to those sources that emit those components, and that would certainly be valuable.
Thank you very much. And in fact, your talk was wonderful, and you have really
thank you for listening.
nicely introduced the various aspects, particularly focused on stagnation. That is a very key, and that's where the high concentrations happens because of the stagnation. And more importantly, you also nicely presented the different scenarios, the co-benefits and cost-benefit analysis. Interestingly, you looked at how the solar energy production can be increased even if you're addressing the pollution aspect. That is quite amazing to look at it the way.
Well, I'm delighted you're so interested. As I mentioned, on my website, you can find the papers that for most of the things that we've done that are open access, and I'd be delighted if people wanted to take a look, and if they can be useful, that would be terrific. And we'd be really interested in staying in touch, because we need Indian input to be useful, and for our work to be in the Indian context. And so we welcome the opportunity for further conversation.
Thank you very much, Professor Denise, and we welcome your group to join our Air Quality Management Association, and we will have longer interactions and long-term collaborations. And I would like to thank your students, Mizu and Z, for helping answering some of the putting their thoughts and sharing their thoughts and valuable inputs to in this talk. And thank you, Professor.
Well, I'd like to thank them as well. They've done some great work.
Yeah, thank you very much. Yeah, I also
okay, great. Nice to see you.
Yeah, thanks all the participants, and yeah, in India it is quite late. And good night to all of you, and thank you. See you in the next Air Quality Management lecture series. Denise, have a good day. Thank you very much.
Thank you. Bye bye.
Bye bye.